Hello everyone, welcome to another exciting episode of Dave Does Math from Home. Today we are talking about how to find analytical limits. So we should probably break down what that means before we start talking about it. Limits we know from the last video that we definitely watched because we're doing this in order because it's very important. If you haven't watched it, go watch it right now. Limits mean what the function looks like it's doing. It's kind of a clever way mathematicians found to sort of cheat the rules and get to talk about things that otherwise wouldn't make a ton of sense, which is very convenient for us because it's what's going to allow us to do calculus at all. So limits means what the function looks like it's doing, and analytical means if you're given a formula or an equation or an expression, we're going to manipulate that instead of looking at a graph. Last section was about looking at a graph, trying to figure out what limits mean graphically. Here we're going to be looking at equations and expressions. So we'll just dive straight into this with an example. Let's say f of x is, let's go with x squared minus x minus 6 divided by x minus 3. Nope, I lied. That should be let's do x squared minus 9. There we go. That'll work. Okay. Hopefully you recognize this as a rational function. We're going to look at the limits of what's going on in this rational function. So the first thing I want to talk about is the limit as x approaches 4 of f of x. So in the last video I mentioned that sometimes what the function looks like it's doing is exactly what the function is actually doing. Those were the very first examples of limits we did, when the limit was just, the function was just doing its thing. It was behaving nicely on a stretch of, we were right in the middle of a stretch of well-behaved normal function. And what it looks like it was doing is what is it actually doing. And we didn't have any problems there. We could just look at what the graph was doing and call that the limit. So that needs to be the first thing that we try when we're evaluating these limits. So, plan A, let me do this. Plan A is plug in the number. So that's all we're going to do. We're going to plug 4 into this function as if we were finding f of 4. And if that works, then we're done. That's all we got to do. So let's see what this looks like. 4 squared will be 16 minus 4 minus 6 divided by 16 minus 9. Looks like that should give me 6 on top, 7 on bottom, 6/7. Cool. The limit of f of x as x approaches 4 is 6/7, and we're all set. We're finished. That's all we need to do. Incidentally, this is also f of 4. That's how we found this. So this is one of those cases where what the function looks like it's doing is what the function is actually doing, and that's going to happen a lot. Be prepared for that. This is the nice case. So let's try something a little more interesting. I want the limit as x approaches 3 of f of x. So once again, the first thing we're going to do here is plan A. We're going to try to plug in this number. And if it works, we're done. So when we plug in 3, we're going to get 9 minus 3 minus 6 over 9 minus 9. That's going to give us 0 over 0. That definitely did not work. Please do not try to tell me that 0 over 0 is equal to 0, or that it's equal to 1, because it's something divided by itself. It's neither of those things. It's not even undefined. It's worse than undefined. It's indeterminate, which is a big frowny face. That means that plan A did not work, and we need to do something else. So here's plan B. Plan B is simplify then plug in the number. So let's take a moment to see if we can simplify this expression. Looks like the top should factor into x minus 3 and x plus 2. It looks like the bottom should factor into x minus 3 and x plus 3, which means that as long as x does not equal 3, we can cancel these, and this function is x plus 2 over x plus 3. So this is the simplified version of the function, as long as x does not equal 3. So here's what's really, really beautiful about limits. If I'm asking for the limit as x approaches 3, x is not 3. It looks like it's going towards 3, but it's not 3. Which means I can ignore this thing that says these are only equal when x doesn't equal 3. I can say, yeah, it's okay. X doesn't actually equal 3. It's just going to get really, 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 really close to 3, but it's never going to equal 3, so don't worry about it. It's fine. So we get to ignore this restriction and basically just plug 3 into the simplified version of this. So this is plan B. The simplified version, as long as x doesn't equal 3, which it doesn't, it's just really close, doesn't equal, so we're okay, is I can plug 3 into this, and that would give me 5 over 6. And that's great, we're done. The limit as x approaches 3 of f of x is 5/6. Some of you may recall in pre-calculus, when we were graphing rational functions, we would take things that canceled from the top and bottom, we would cancel them out, we would graph this, but then we would still include this sort of domain restriction that got canceled as an open circle on the graph. It's a little open dot to represent that x still can't equal 3, but aside from at that exact point, it doesn't matter. If we were to graph this, the y value of that open circle dot at x equals 3 would be 5/6. So that's really what we're doing with this limit, is we're finding out where exactly these dots go in functions that have little open circle dots in them. When x is actually equal to 3, the function is undefined. There's no value at that point, which is why it's an open circle. But the open circle goes here, which I think is pretty cool. We're going to do one more limit on this problem. But I need to erase these things first. It's time now to talk about the limit of f of x as x approaches -3. So in this one, we're still going to start with plan A. I know that I have a simplified version of this right here. I'm not going to use the simplified version. Every time you do a limit, you need to start with plan A. The reason for this is later, when we get to section 2.6, I think it's section 2.6. When we get to a section later in this chapter, it's going to be extremely important to know which plan worked. So we're not just interested in finding the numerical value of this limit. We're also interested in knowing which plan got us there. Because if you find something with plan A, that gives us different information than if you find something with plan B. In that last problem we did, because we had to go to plan B, that's how we know that there's an open circle on that graph. If we skip plan A, we'll still get the limit. It'll still be the same number either way. But we won't know whether or not that value is an open circle or a closed circle dot thing. So it's important to know which plan works. So we're going to start with plan A. We'll plug some stuff in. This will give me 9 plus 3 minus negative 3 will give me plus 3 minus 6. So it looks like a 6 on top. The bottom should give me 9 minus 9, which is 0 on the bottom. That's a big frowny face. That's not going to work for us. 6 over 0 is no good. So we're going to switch to plan B. I already have the simplified version here, x plus 2 over x plus 3. This is as simple as this possibly gets. Can't simplify it anymore. So I'll try plugging x equals negative 3 into the simplified version. That will give me a negative 1 on top and a 0 on bottom. It's going to be another big frowny face. Which brings us to plan C. If plan A and plan B both fail, there's still one thing we can do. Give up. When you get to plan C, you know that the limit does not exist, and so you're done. Graphically, x equals negative 3 is a vertical asymptote for this function. So the function doesn't look like it's doing anything. That's why the limit doesn't exist. It's going to be doing, there's x equals negative 3. It's probably doing one of these numbers. So it's on one side of negative 3, it's plummeting, or sorry, negative 3. There you go. On one side of negative 3, it's plummeting down towards negative infinity. On the other side of negative 3, it's rocketing up towards positive infinity. Neither of those things is a number, and also they don't agree with each other, so this limit super duper does not exist. There is no number that this function looks like it's getting close to. It's going berserk. So plan C means that the limit does not exist. If you can't simplify it into a more well-behaved version of itself and get a value out of that, then there is no limit at all. This is it, the plan A, the plan B, the plan C. I'm going to cut this video here. We're going to make another video so we can practice this more and talk about some other ways that we might have to simplify some functions to make them a little more well-behaved. But for now, this is a good start. We got plan A, plan B, plan C. We're good to go.